Okay, it starts.
All right. So the title of this talk is kernel learning for attention mechanism. So I guess okay. So there's two parts of the title: this kernel learning part and the attention mechanism part. So this is based on a survey which I'm working on with Dr. Aditya Joshi, my supervisor, on kernel methods in transformer. So kernel learning is basically something to do with kernel and kernel machines. Attention mechanism is basically something to do with transformer. And I guess the motivation for the talk is transformer basically completely transform the landscape of NLP and deep learning over the past 6 years. So it completely replaced CNN and RNN and LSTM in NLP, but there's not a lot of theoretical foundation for transformer. So the main reason, some say that the main reason for building transformer the way it was because they want to saturate GPU, because by building simply attention-only architecture, you can parallelize all computations, which would saturate the GPU. So in recent years, there's been some work regarding the theoretical foundations of transformer, how do we understand it, how do we generalize it. And some have just suggested that kernel is perhaps one of, perhaps a way for us to understand transformer and attention mechanism. And so in order for it to be a useful framework, it has to satisfy two criteria. So number one is that it has to make transformer easy and intuitive to understand. And secondly, it has to make transformer generalizable, and it has to show that different forms, different ways to manipulate transformer is still at the end of the day transformer. So and we can use the framework to show performance. So I guess that's the basis of the talk. So we'll explore how kernel can contribute to a deeper understanding of transformer and whether it's a generalizable framework. So I guess before we go into the more technical stuff, I kind of want to ask about everyone's sort of experience with deep learning, so I can see how much I should assume and how much I should explain. So I guess do you understand any of these terms? How about you?
Kind of.
Kind of. Do you understand what a perceptron is?
No.
Okay. Do you understand what gradient descent and back propagation are?
It just looks familiar, so.
Okay, you're not familiar. Okay. So we're gonna go through it really quickly before we jump into the main section of the talk. So let's say, look at the picture on the left. Okay, so this is taken from the deep learning book, the definitive deep learning book. So on the left, you have two data points you want to separate. So you have the green triangles and you have the blue dots. And so now our purpose, what we want to do is we want to do a binary classification task where we want to separate the green from the blue. And specifically, we want to have a linearly separable line or surface. So if you look at the left side, so given the x, y, and y coordinate, we actually cannot separate these two dot points with a line. But if we transform them into the polar coordinates with theta and r, then we can easily separate them right in the middle. So the point of this being that in machine learning, when you want to do any task, the way that you represent it matters a lot. The left is Cartesian coordinate, right is a polar coordinate. So a more specific example, especially in the case of deep learning, is, for example, this picture. So you want to do, that's object classification on an image, and you want to detect that this is a person, and you have three output categories: car, person, and animal. So I mean, you can just put this image through some sort of thing, right? And it would just try to figure it out. But a better approach would be to, first of all, feed it through. So you can see the first layer. Feed it through the first layer. The first layer extracts the input cells, pixels, into edges, and edges go and extract the corners, and all corners extract further the object parts. And then maybe it's able to figure out, oh, if it has like a structure of a nose, then that's probably a person. If the nose is a bit longer, it's probably not a person. So the point is, we want to keep representing things, and then we're going to derive a better representation of that represented thing, and we keep doing that in recurrence until we get it to a level where it actually represents all the information we can use to do our task. So one way of doing it would be to use perceptron. So in machine learning, there's a lot of different ways. Deep learning is just one, right? So perceptron is a very basic model to try and do this stuff. So given 3 inputs, the top would be like x1, x2, x3, and you draw an edge from x1, x2, x3 to the sigma sign, and then you have an activation function of 2 outputs. So this would be, so what can you do with this? So let's say you have 3 inputs. Let's say these are the height, the width, and the price of the house. So let's say those are the 3 inputs, and and you want to predict whether this house belongs to, let's say, a rich person or a poor person. Let's say we're living in a world where there's only rich and poor people, and so you have 2 outputs. And so when you check the output, you just check what the first one represents rich people and the second one represents poor people. So if the rich one is more than 50%, then obviously it's the rich one. If it's less than 50%, it's obviously the poor person, right? So to do this basic model, we simply feed the 3 inputs, and we times it by the weight. So x1 times w1 plus x2 times w2 plus x3 times w3, sum it all up. So we get sum, and we have an activation function. So an activation function, well, in this case, if we do binary classification, we can use a sigmoid. Well, basically, it's a function which just applies on it so that we can get some output that we want. Specifically, we want to get a probability output over here. So we can use softmax to get probability output. So that's a simple case. Now, we can keep combining it. So let's say you get one output and you keep doing another output. So in this way, each layer, you're getting a better and better representation before you get to the final. Because maybe if you just do one layer, you're not going to be able to get everything you want. So I think I can introduce some concept from deep learning, and that's called universal approximator theorem. And what this theorem states is that with a neural network, just one hidden layer. So it's so this one has 2 hidden layers, but let's assume that this only has 1 hidden layer. The universal approximation theorem states that if in a 1 hidden layer you have enough nodes, you can actually approximate any single function you want. And these are nonlinear functions. So if you imagine the output of a human, you can think of the output of a human, our language, to be a nonlinear function, actually. Then it can represent a person, predicted output, over their entire lifetime or whatever. So why don't we just use one hidden layer? Well, the issue is if you use one hidden layer, if you use only one hidden layer, then the number of nodes in that hidden layer would be too many, so you want to sparse it out. And secondly, you can overfit. So I guess that's the point of having this multi-layer perceptron. So this will be the foundation to do any building block that you want in deep learning. So, okay, so this would be how you calculate. So how do you, I guess the point is, well, that's how you can, this is the function, but how do you find the weights, right? Because you need to get the right weights and then get the right outputs. Because at the start of the training, you initialize these with random variables. So to train, all you do is you do what's called backpropagation. And to do backpropagation, what it is that you define a loss function, and let's say the output of this is
maybe. Yeah. Yeah, RSA. Yeah. Just on it.
So So yeah, so to do back propagation, all we have to do is we define a loss function. And so let's say, and the loss function calculates how off our estimation is. So let's say our estimation is that it's true, but the actual answer is false. So you can do some sort of one simple, if you use from regression, right? You just take the absolute difference between the two values with classification. Then you can do binary cross entropy. It's like some entropy function to calculate the two. And then afterwards, once you get the difference, you can take the derivative of that, and then you calculate the derivative from the last in layer to the previous in layer, all the way to the back, all the way to the front. And then you would be able to update the weight using the derivative, basically. So let's say you're at this black point, and the gradient is in dots. So you want it to go down, because when you go down, you minimize the cost of the loss function. When you go up, you maximize the cost of the loss function. So you take the derivative, and then you just minus that. And you minus it with an alpha, because if you minus it too much, it might go like this, and then it might go like this, this. So it will never converge back to the true minimum. Another issue with gradient descent is we will never get this scenario. So this is what's called a convex function. A convex function only has one minima, and the minima is local and global at the same time. In reality, the gradient descent landscape looks something more like this. So let's say if you start from, the true minima is this one on the left here. But actually, if you perform the gradient descent algorithm, you actually end up on the right one, which is the right local minima, which is not the true global minima. So in deep learning, we sort of only try to, this problem is like really hard to solve. There's like different ways to go about it, but really what you want to do is you just want to get to local minima and assume that's good enough. So that's the start, and now we're going to go into the actual thing. So before that, does anyone have any question? Got it?
I kind of get the definitions here.
Did you understand the definition?
Yeah.
Awesome. So okay, so what are we talking about today? So with kernel, so here, as you can see, this is a direct acyclic graph, and we're gonna build up every single foundational concept, and then we're gonna connect them, and then we're gonna finally understand what's the point of all of this, right? What's the point of kernel? What's the point of kernel in transformer? How does it help transformer at all? How does it help us understand transformer? So the table on the left shows the order of the topic that we'll be going through. We're going through first kernel NP means non-parametric, kernel in a non-parametric statistics sense, kernel PD, which is the positive definite kernel, GMM, which is Gaussian mixture model, transformer, which is what we are discussing today, and we're going to be discussing 3 other papers, Tai et al., Rahimi and Recht, and Chowdhury et al. Okay, so first a recap of all these basic foundational concepts. So basically transformer, kernel, 2 different definitions of kernel, and GMM. Alright, so to discuss about this, let's go back to the start. Let's go back to a very simple problem. So this is the Google keyword search from the year 2004 to current day, and this is for the term sugar in the US, and you can see 2 sort of trends in this data. So number 1 is we can see a seasonal trend within the year. It sort of goes up and down like this, but you can also see an overall trend of just the sugar term going up in general. So now, what we want to do is we want to, let's say we're a company, and we want to see that actually sugars in general it's going to going up. But if you just compare this point to this point, for example, it seems like it's going down. But that's not what we want, right? So what we want to do with this graph is we want to do some sort of smoothing to get the actual overall trend. And so this is called linear smoothing, and we're going to connect this to linear regression, which is where you're given an x and you have to predict an y. So given a data set of x and y, so given x1, xy1, x2, y2, blah, 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 where y is a real value and x is a p-dimensional vector, then the linear regression model assumes that a given point y is equal to a function r of x at that point plus epsilon I, and that is defined to be the sum of beta j times xi over all dimensions from j to p plus epsilon I. And I is like 1, blah, 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 n, where the expected value of epsilon I is 0, and variance is equal to sigma squared. So Gaussian, right? But basically, so then we would say that R is an unbiased estimator of Y. Why is it called unbiased? That means that, well, okay, so when you measure things, there's definitely going to be some error margin. You can't measure things precisely. We assume that the output that the thing that we measure in real life is actually not the real value. It's actually the real value plus some noise. So we actually say that R of xi is the true value. And if we minus all the, so it should predict the true value without all the noise. So epsilon is just all the noise. Unbiased estimator means that it will predict the average value at that specific position. So if you think of like the entire data set. The X is the entire data set, right? So the rows are the features, the columns are the features, and the rows are the data points. Right? So first, second, third, the first feature, second feature, blah, blah, blah. And now beta, we think of beta as a vector, epsilon as a vector, and y as a vector. So now we have basically all the data sets, all the weights, all the error terms, and all the y's. Then we can rewrite equation 12 as follows. yi equal to rxi plus epsilon I. And the same thing, right, with the b term. Then we can rewrite this as y equals to x beta plus epsilon. And then we can take the epsilon term to the left and then y to rearrange it, and you get epsilon equal to y minus x beta. And if we can minimize this epsilon, right? Because we want to minimize it. If we minimize it, then we'll get an unbiased estimator. We're trying to figure out the beta. So we just basically square this whole thing, we get this, and now this is like sort of, and then you just, what you do is you take the derivative of this with respect to beta, and you set it to 0. And then you solve for beta, because at that point beta, this equation would be at the minimum, right? And it's a convex function, because it's a convex function, so the beta would be equal to the minimum cost. So, but we don't need to do gradient descent, because we have the equation and everything, so we can solve for beta hat, which is equal to x transpose x inverse times x transpose y. Refer to Vassman 2006 if you want to see the detailed proof. This is assuming that x transpose x is invertible. Hence, the estimate of Rx at x is equal to R hat n of x is equal to x transpose b hat. And then the fitted value, right? So what we think is the unbiased output is going to be R equals to x beta. And then if we define, so if you see, you define all of this as an L term, then you have L times y over here. So, yeah. So now, if we assume that the hat matrix L is symmetric, symmetric means that it's equal to its transpose, then we can define an Lx function which corresponds to one row of the L matrix. And then if we take the transpose of that, then we can rewrite the same thing here. Instead of having this x, big X here, we put the small x transpose in and we get the Lx transpose. And if we put that into our equation, then we get Lx R hat n of x is equal to Lx transpose y is equal to sum from I to n of Lix times yi. So this is a pretty important definition. So we call the estimator of R and a linear smoother if for each x there is a vector Lx equal to L1 to Ln transpose such that the above this equation satisfies. So this is the definition of a linear smoother. So this is exactly what we want to solve our sugar problem. Note that this is a little bit different. This Li, because we're doing transpose here, so if you look at this beta, this operates on the feature, this does not operate on the feature, this operates on the data set, data point. So for every single data point, we have a corresponding Li such that the value of x is equal to, well, Li times x at every single data point. So you can think of it as like, you have one point, you give it that x point, and then you apply Li on every single data point times y. You sum it all up, and you get back the x. So kind of a weird way, instead of like this. Okay, so now we're going to introduce something and we're going to combine it together. We're going to introduce a concept of kernel. But this kernel, note, is strictly in the non-parametric regression sense. So a kernel is simply a PDF. It's simply a probability density function. So, of course, at any given point, it's larger than 0, and it integrates to 1. That's the basic properties. And then, but really, you can think of it as a weighted sum. So let's say, okay, so let's try this. Let's have this Li equal to this over here. And then, if you have kx equal to x, that's going to be the original graph, right? But if you have this equal to this over here, then this point will be equal to this, plus this, plus this, plus this, divided by 1 over n. How many n points there here? So it's a moving average. So it's smooth thing. But if you do like a Gaussian, then the further you get to the central, to the point, then the higher the weight. But the further you get away, the less the weight. This is like a weighted sum, but it takes into consideration the distance. So now, net area in Watson 60 years ago showed that Li can be defined this way using kernels. And you have Li of u is equal to k of u minus xi over h, we'll talk about what h is, divided by the same term in the numerator, but sum over all j in the xj term. So this is the net area Watson kernel estimator. H larger than 0 is the bandwidth. So h controls how smooth it's going to result in the final graph. The larger, I can't remember exactly, but the larger, I think the larger the h, and the smoother it's going to be. And so you can think of it as it's applying a moving average on every single point. Yeah. And so if you apply the Gaussian kernel on the sugar data sets, this is the graph that you get. So good. Okay, switch gears. So now we're going to talk about the kernel trick in SVM. So this kernel is a different kernel. I don't know if you guys have heard of this, but okay. So given the same problem we had before, right? We have we want to separate this with this, and we need to find a decision boundary. There's no decision boundary here, so we have to apply a linear map on each of them, and then we can immediately be able to identify the decision surface. So this is called the kernel trick. But the kernel trick really is composed of two things. Number one, you transform each of this into the 3D, and number two, you calculate the distance between each of this, and you're like, oh, well, this is the furthest. Oh, this is the way the points are closest. So you draw a decision surface right at the half midway point between what these are called support points. But a more mathematical definition of it is a kernel is the dot product of a linear map applied on two vectors of the form k of xi equal to phi x phi y. Right. So now go back here. So that means apply phi on the green, phi on the red. I mean phi. I'm sorry. So x is axis, y is axis. Apply phi on each of this. Wait, I'm sorry. X, y are any two different points. So apply phi on every single point. Apply phi on every single point. Then take a dot product between them. Find a distance, And we can find all of this is like close to each other. This is the most difference because the dot product represents a distance. And then, yeah, find the support and get that. So what is the kernel trick? The kernel trick is that instead of trying to find what's the suitable phi, and then trying to find the decision surface, we can instead just define the kernel and don't care about what phi is. Right? So for example, this is the Gaussian kernel. So this is the kernel, but we don't know what phi is. I mean, I guess you can do some reverse stuff, but it's really hard. The reason for that is because this is infinite dimensional space. Gaussian kernel operates on infinite dimensional space. It doesn't map to this space. You can't even imagine it. So Gaussian kernel in particular, it works like a K&N. But yeah, the kernel trick is you don't need to calculate this explicit phi, and you can simply calculate distance. Okay, so I mentioned before that kernel ties into transformer. I guess I'll mention something about this kernel that makes it clarifies the point why we're using it. So usually to do any sort of this stuff, you need to calculate k on every single pair of points. So that's quadratic, and that's going to create what we call a gram matrix. So you have all the x point here, x1 to xn, and you calculate all the distance between them. So yeah, so it's quadratic. It's not good for us. Anyways, we'll talk about what we're going to do about it later. So kernels are typically symmetric. So k of xi, k of yx. Obviously, it's a distance measure, so that's guaranteed. It's positive definite or non-negative definite. So this is just a mathematical convenience. What that means is that its gram matrix is non-negative. And for a gram matrix to be non-negative, that means that, well, first of all, the matrix has to be square and symmetric. And secondly, it has to be non-negative. So all of its eigenvalues are non-negative. So yeah, I hope that's pretty straightforward. 101 linear algebra. So now we have some special class of kernels. So the Gaussian kernel, as I mentioned before, many of these special kernels are shift invariant. What that means is that they don't care about the x and y point individually, they just care about the distance between x and y. So k of xy can be defined using a k tilde of x minus y. So let's say x plus 1, y plus 1, distance is still the same. So this will be another important point we'll come back to. Okay, so now for the final, before the final topic, we'll get to the meat. So the Gaussian mixture model. Okay, so this is really interesting. So we have this black point here, and this is a PDF. This is a probability density function, and we want to approximate this, but we can't approximate this with one Gaussian. Look at it. If we just get the mean here, do the plot over here, that doesn't look like it right at all. It has so many so we don't do it with one Gaussian, we do it with 4 Gaussians instead, right? We have this one, this one, this one, and this one, each with a different mean and sigma, and actually, so we just plus it all together. So each of this is each of the Gaussian, and each of them has a different weight. So this one is 0.53, which is at 10.58. So this one contributes to the most weight, probably because I don't know. Anyways, you just need to define some function, which you define a number of components, a number of Gaussians, and then you can easily learn any PDF that you want. So this will come in handy later when we want to learn a PDF.
Is it like a normal distribution or?
Yeah, Gaussian is just a normal distribution.
But what is the W on the right side?
W is the weight. So we're going to sum all of these together. Yeah, to get the distribution. Yeah. So yeah, a summary, the points. Okay, first of all, non-parametric kernel. What is it? It's a function to reweight the value of a point on a graph by considering its neighboring point for smoothing. It's like a moving average. So the value of the point depends also on its neighbor. The second one is a positive definite kernel. In the kernel methods used in SVM, it calculates the distance between 2 points in some high dimensional space. And finally, we have GMM, which estimate PDF using multiple Gaussians. Does anyone have any questions so far? You just joined. So it's say anything. Have you heard of non-parametric regression?
Yeah, I guess just because I did mention it years ago, so still get it.
Yeah. So I guess like at the beginning. So I guess like I was just seeing you joining here. But before that we were talking about. It's just very like non-linear regression.
Yeah.
But basically we define a subclass of linear smoothing and non-regression called the Nadaraya Watson kernel estimator, where you define the linear regressor using a kernel. A kernel is just like a PDF, and it helps you calculate point using its inputs. So that's all that we've covered so far. And before that, we went through some basic deep learning stuff. Okay, so now to the part that you're all here for, transformer. So who's familiar with this? Cool. Are you guys familiar with this? No. Okay. So how would you explain a transformer?
Let's fill it up.
Okay. So a transformer, so it was proposed by Vaswani et al. In 2017, right? It was, in the original paper, it was proposed as a way to do neuromachine translation, NMT. So translating, right? In Google Translate. I think of it like that, what it is. And so basically, it's a machine translation task, but at the end of the day, it's a sequence-to-sequence task. So you give it a vector, it gives you a vector, but not in the sense of classification, more so in the sense of sequencing. So the order, there's some thing to the order, so on. So with this model, it's basically composed of stacks of encoders and stacks of decoders, right? Je suis étudiant. I'm a student. Perfect French. And each encoder block, so this is encoder block repeated n times. Decoder block repeated n times. Okay, so I'll run you through very quickly how this kind of works. So you have an input, let's say you have the original sentence, you embed it, right? So one simple embedding scheme is, let's say there's 500,000 words in the English dictionary. Every single word you represent it as one hot vector with dimension equal to 500,000, right? So let's say V is at position 0, so position 0 would be 1, the rest would be 0, right? Or A would be position 2 would be 1, the rest would be 0. That's one naive way to do it. There's like other more complicated embedding scheme. Positional encoding is basically a way to differentiate between the same words but at different position. But it applies on everything anyways, because we don't care. For example, if you say, I'm going to the bank, near the riverbank, obviously the two banks are completely different. So you need to encode position into it so that you can distinguish it. And then you pass it through this encoder block, and encoder block has this multi-head attention, add a norm, feed forward, add a norm, repeat it n times, and then feed it into the decoder block. So, okay, and then we have this, and then feed it to linear, and then softmax, and alpha probability. Okay, so what the hell does that all mean? So we'll look into what multi-head attention is later. But multi-head attention, at the end of the day, it's a way to calculate. So multi-head attentions means multiple blocks of attention. Attention is used for calculating relationship between words. Multi-head attention simply means different weights of calculating different sets of relationship between words. Maybe for some head you want to calculate similarity, maybe for some head you want to calculate difference, maybe something you want to calculate something else. So to extract all sorts of relationship between words. And then you go add it through what this is. Add is addition and normalization. So this is what's called residual connection. Residual connection is used in deep learning. Why? Because, so let's go back to the beginning slide. So when you do backpropagation, you have to calculate the derivative. When you calculate the derivative and you use the chain rule, actually the further back you go, the weight for each of the edge becomes smaller. And if the network is too long, then the weight becomes so minute that it doesn't come up in the final calculation at all. So this is called the vanishing gradient problem. And so to avoid that, you need to basically, instead of linking this one to this one, we just link this one directly to this one. So to avoid that. So that's called residual, and it's here denoted as add. And normalization is just to normalize it with mean of zero. With mean of zero as an indication of something.
So what's inside the outputs, the shift to right one, the input output, I mean the input outputs from the right quadrant.
So which one?
The lower in outputs, shift to right one. Label shift to right.
Yeah. Shift right. We're not discussing this yet. We're not discussing it yet. We're just talking about this one block. Yeah, and so basically you have the sentence, you embed it with all the stuff, you calculate the relationship between the words, and then you have the residual function, you have normalization, and then you feed forward. Feed forward is just like adding about like just one fully connected layers, and then you have this one. So after you get this one, you get one representation of the same sentence, but now with information about the relationship between the words.
Wait a second. So for the input dictionary, it's like a one-to-one. There's every one-to-one corresponds one from French to English, right? There's like there exists like
for every word.
Yeah, for every word.
No.
So the connection hasn't been established until the like.
So we haven't got to that part yet. At this part, we're only feeding it only the English one.
Okay.
Or the French one. Let's say with the French one. We're only feeding it the French one, and we're only trying to find a better representation of the same sentence, but embedded within it are the relationship between the words in that sentence.
Okay.
So yeah, and then you just do it n times. So you keep finding more and more, like relationships between that. And once you're happy with that, you put it through this thing. And so now I'm going to explain a decoder block. And the decoder block is basically so basically you put in, okay, so this is not exactly the right way to say it. I'm going to say it this way so it's easy to understand. So imagine you have an input into this output emitting, and it's the translation. And you have it, you do all the same thing, and you do all of this the same thing. But this was what's called mask multi-head attention. What mask multi-head attention means is that you don't calculate the relationship between words if the words are afterwards. So for example, if I say I want to go to the beach, I only calculate, so if I say I only calculate I and I want to, then I want to calculate together, don't care about go to the beach part. And we want to do that is because we want to do prediction, we want to generate predictions on the sentence later, and so we don't want the information of the future parts of the sentence to leak into the word representation. So that's the whole point of this mask thing. And then afterwards, we calculate this thing is called cross attention. So basically, we take the query from here and keep it. This is pretty complicated stuff. I can go into it more in depth later with illustration. But just understand that basically we calculate the relationship between the words from the original sentence and the translated sentence. And we feed everything through here, and we have a linear layer so that we can have one. So that it's just like normalized through one thing, and then softmax. Softmax is just a way to calculate probabilities. So basically, if you have a sentence like I'm a student, it will just generate the softmax. So let's say the highest probability will be the first word of the translation, and then after you feed, and then it keeps generating until you reach what's called an EOS token, end of sentence, and then the translation is done. So that's an overview of this thing. Yeah, so this is the equation for calculating attention, which is calculating the relationships between words. So it's calculated as, so there's three components per key and value. Okay, so how can I explain this simply? So at any single point, so at this point, this attention is called the attention matrix. So it's for the entire thing. But actually an easy way to think about it would be to think about it at the level of a single word. So when you're calculating attention for a single word, you're actually only using one query. Okay? So you're comparing one query to a bunch of keys. Keys are the representations of the other words, contribution of that word to this one word. Maybe it's better if I show this. Okay. So the cat sat on the mat, the cat lay on the rug. So we have, this is the input and this is the output. So it's the same thing, it's pretty simple. So this is, you can see this, what layer is this, what head this is. Let's say we want to choose this head. Yeah. So if I go to cat, okay, cat is still cat. Okay, I guess I can do this one. So if I do this one, you see that there's a different edge color. The brighter the color, that means that the more of the contribution of that goes to length. So for this head, the connection between steps is separated. It could be like a comma or a dot. So it contributes stronger to the meaning of lay. Okay, so we have sat, sep, set. So these contribute to the meaning of lay. And you can see how that is by looking at this. So the lay, so we put in a query, and then we find that when we times q with k, we take the dot product, element-wise multiplication, we find that they have the highest point. So we take that and we times v. And v is just another representation of lay. And so it's something like expected value, right? Expected value given a different key. Yeah, so I guess that's, but when we get to the kernel part, I can sort of make it more simpler because right now, this is from the original paper, so it's very hard to understand. All right, so now we have transformer. Transformer is built simply based on just the attention block, right? Just all of this attention block. So it's pretty crazy. So to describe the relationship between words in a sentence, relationship between words in a sentence can be accurately modeled using attention. Okay. So now we're gonna talk about tie. And tie, I'm gonna take all of these three things that we just discussed and discuss like how kernel has a role to play in transformer. Now this paper was published in 2019. It got around like 100 citations, and it's pretty influential because this paper inspired linearized attention model in transformer. What the hell is linearized attention? Because attention is quadratic so O of n squared to the length of the input. But linearized model makes it less than that. It can be constant. Yeah, and so that's using the kernel formulation. So let's look at that. So given a sentence, right? Let's say, okay, let's start with the example. How are you doing? So how would the 0th one, I would be the first one, you doing, so on. So each of them can be composed of like two different representations, right? The actual word representation and the temporal component. Because you know how we have before, we have the embedding and the position embedding, right? And then they both belong to these two sets, and we can define this as the joint set of f and t. But then you also realize that when you're calculating attention, you're calculating it all at the same time. So we can define it as a set, permutation invariant set. And the temporal component, the position component is embedded already. So you don't need to care where it is. So I guess that's that. And now back to the query key and value, right? So for query key and value, we have query key and value, which are different representations of the same word, right? But the query, you use the query to compute the relationship with the other words using the key, and the total value will be equals to the relationship between the query and each of the key times the value. So you can think of query times the different keys as like a probability, and we'll see that. So it's like an expected value. So given, okay, so in self-attention, the xq and xk are the same. In cross-attention, they're different. So in self-attention, so when you're doing like self-attention here, it's the same value. Here, it's the same value. But when you do it here, the query takes from here and the key takes from here. That's all it is. And so given this softmax equation, softmax is just equal to e times to the power of some value, divided by the sum of e to the power of all possible values of the same thing. And then we can define attention for a single query, given a set of keys as the softmax of that query times the query matrix times the xkwk transpose divided by dk softmax times xkw. So this is the value, this is the query, this is the key. If we define all these to be different, then this weight matrix really is the thing that's learnable, and this x is not. This x, q, k is not learnable. And this is just like a way to this square root of dk. It's just a way to basically normalize it.
So where are these generated from? Like are they like just have like I don't know, just how those just d comes from?
So dk is equal to db equal to d model over h, which is 64. So d model is the dimension of the token of each word. So the dimension in my example was 500,000, right? And h is simply the number of heads. Yeah.
So you just fix it.
Huh?
Is it basic physics?
Fixed? It's fixed, yes, it's fixed.
Okay.
It's fixed. It's fixed. It's not learnable. Right? And then in the original paper, xi is defined as fi plus ti. And this is strange, right? Because why the hell is it fi plus ti? Like, could be like multiplication. Why is it addition? So let's do something funny. So this softmax, we can rewrite this whole thing as the numerator and then this whole thing as the denominator, but like over all possible value, right? And then if we define this thing, we can define it as a kernel. So let's define it as a kernel. So that's simply the dot product of these two, right? Variable transpose and the dot product of these two divided by this. And let's define this as a v of xk function, where that's simply xk times the wv matrix. Then we can actually interpret this. Okay, forget that as m for now. Then we can interpret the original equation as simply the sum of xk over k divided by all possible sum of k times v of xk. And you see it's true because this one is this one. This one is this one, but in the numerator term. This one is this one, but in the denominator term. So it's the same equation. So you should notice something because this thing is this thing. It's the same thing. It's the Li. So this is actually another area of Watson kernel estimator. So they just showed how attention is actually what? Linear regression. So we're giving it some, but of course like there's a difference because this k, the other kernel it takes only one value, and this is it's supposed to be a non-parametric kernel, but it integrates to one, but this is not a non-parametric kernel. This is like a positive definite kernel. This is a measure to measure distance. So it's a little bit different. And then so you have this thing, so and this would be equal to y, right? So x equal to Li of x times yi. So you can also think of this as p of xk and xq because this is with this specific xk, but over all possible value of xk, given that xq is the input for this one. So it's actually the expected value of v of xk given probability of xk and xq. Yeah. So yeah, it's actually some sort of regression stuff, actually using like some kernel. So if we look at it this way, then what is it? So it's the expected value given some way to measure the distance between words. So what this implies is, well, first of all, why the heck is this kernel defined this way, right? Maybe we can find a better kernel. Maybe we can find a kernel that, because the justification for this in the main paper was just to, this is fine, and this is to linearize. This is to normalize. And this EXP in the original paper, actually the only reason why this exponent term was thrown in was because it was to stabilize the output. And just one more thing, this M would be equal to the SXK most of the time, but it has to be here because when we're doing decoder self-attention, if you notice, it's masked, so it doesn't attend to the number, to the words after it. So that's why you need to throw this in. So because of this formulation, so it opens up a lot of stuff, right? First of all, what's the way to compose this? Because this is just one way. There's other ways you can compose this. Secondly, k value. Thirdly, the v value and the set frame function n, because there's probably other ways to do the set frame function. So, based on this, they're able to identify all the different ways that you can classify all the different transformers variants based on this formulation. For example, set transformer doesn't use the temporal component. Okay. Image transformer has a high and width component. Multimodal has the linguistic, vision, and audio components. And then we have the different ways to calculate the kernel function, right? I'm not talking about so of course there's this way, which is the dot product of these two divided by square root of dk. But I'm talking about how we can compose the embedding in the temporal component, because you can compose it like this, which is really weird because usually you do it like this, right? F plus t and F plus t, and take dot product and then calculate that. But actually you had to do the 2f together and the 2t together and then dot product of that. So there's a much wider space for how you can approach this computation. And then, obviously you have the value functions. Doesn't really matter. But some people like to not have the TK, the temporal component. So they'll investigate whether this is useful or not. And this is just a set frame function. Most of it you don't need to care about. It's just so for all of this, I already told you how it works. For some of the other models, they even make in the decoder self-attention, they make the parts to attend to even smaller, or they add some extra stuff. Yeah. So here's the model design. Here's the one that they think that will probably perform well, where calculates. Well, it's basically this one. It's basically a relative position and thing. Yeah. But one thing they did was that they have this normalized. So they have all the weight matrices normalized. Not normalized, but the same thing. They don't have very key value. They have all the weight matrices the same. So yeah, they're proposing some pretty radical stuff about how the liberty of which you can change the way that how these things work. And then of course incorporating position embedding. So it's separate. Just looked at. Okay, results. So they found that when you incorporate position embedding, and instead of doing a direct sum, which is like this, which is in the original paper, if you do it like this, you actually get a better result. Look at both of the product. So for neurovision translation, blur score, the higher is better. For SP, which is set sequence prediction, the lower is better. So this is good. So this is bad. They shouldn't have done this. For kernel types, test on all different kernels. RBF is kind of similar to the, well, I guess it's basically RBF. It's basically what the original kernel was. Or was it more like exponential? Yeah, it's like exponential and this is RBF. So this is, so instead of doing a dot product here, just take the difference and L2 norm and then square it and negative over here. So what's the conclusion? Conclusion is these two are not so good, these two are great. Why? Seems to be the common denominator between these two is infinite dimensional. So maybe infinite dimensional gives us what we want. And this is just some more nerd stuff. You don't need to care about. But finally, with the v function, well, whether to incorporate t or not doesn't matter. So yeah, kernel choice matters. Product kernel gives the best performance. Decoder substitution is not ordinary. This is the thing I skipped. And precision embedding valid function doesn't really matter. And yeah, this is why this is a good formulation, because shows that it shows that we can decompose it and we can try different things and it's still pretty good. And depending on how you do it, you can see the change in performance. So this is a pretty good framework so far. And it can also be used to categorize all the different variants and finds a larger space for how we can construct transform the variants. Yeah, conclusion, kernel is an appropriate method to decompose attention. So now we have these three. So now we're going to finally look at Rahimi rect and see how that's going to ultimately help us do some, well, I mean, like, it's already foreshadowed, right? If you have this, because it's a kernel, and there's a heaps of methods in kernels, right? It's been around for so long, but like 15 years or something. And so we can apply all these techniques to our transformer to make it better. So one of which is kernel learning, right? And spoiler alert, kernel learning has to do with this figure. If we combine these two, then we'll get the thing that we finally want to get, which is to learn the kernel of the transformer. So okay, so this paper, this is pretty awesome. So what's your background?
Background?
Yeah. Mathematics? Cool. All right, so this paper, so I was asking that because this guy is photovoltaics. So, and this paper involves Fourier features. It involves Fourier transform. And it's pretty mathy. So, okay, so this paper is Rahimi rect, random features for large scale kernel machines. This paper is really, really cool and really, really important. So this paper was published on Advanced Neural Information Processing System in 2007, and in 2017 it won Test of Time Award. Why? Because it was awesome. And the reason why it was awesome, actually, the author in his speech, in his award speech, he was making fun of other models, and the way he was making fun of them was that he was saying that a lot of models these days are alchemy, because there's no theoretical foundation for it, right? Which is test it. Oh my God, this looks great. I can publish a paper with this. That's all they do, and they don't try to And the thing is, if you do that, you'd have no idea about in which conditions would work and in which conditions it won't work. You're just overfitting on the freaking data set or something. You don't know. So the reason why this paper is so awesome is because it uses some theoretical findings from mathematics, and obviously it's pretty complicated, but from the theoretical findings, you can do some basic math to produce some really, really, really powerful machine learning techniques that will change kernel methods, basically. So, okay. So now you know it has something to do with kernel methods. Okay, so I already said kernel matrix, scales per drive with data, so you can collect every single data point. Another method that's also used is called linear SVM, where you explicitly calculate the feature map. If you explicitly calculate the feature map, you only need to calculate the feature map once, right? With the other one, it's quadratic always. So the proposed approach is to, okay, what is it? You want to approximate the feature map given a kernel, right? So what's the proposed approach? Convert training of kernel machine into a linear machine by mapping data into low dimension randomized feature, reducing competition from competitive. So more concretely, right? You know that your kernel is composed of the dot product of phi x and phi y, x and y in d dimensions. So because, well, this is a dot product output, so of course it's a real number. If it's a real number, then we can approximate with two lower dimension feature maps, z and z, where this r, which is the dimension, which is the actual output dimension of z, is a lot smaller than this phi, right? And this method is used to approximate shift invariant kernels, so the class of kernel which I talked about before. And with the dimension of r equal to this term over here with some error term epsilon here. Okay, so I'm going to run through proof from a blog post from a scientist named Gunderson, researcher Gunderson, and the reason for that is because the original paper doesn't point out all the proof because he just assumes that like people just look at this and immediately realize the proof. There's a very small proof section, and the main character in the proof is Bachner's theorem. So Bachner's theorem, a result of partial differential equation, states that a continuous shift invariant kernel, k of xi equal to x minus y, on R D is positive definite if and only if k delta, so this difference, is the Fourier transform of a non-negative measure. Okay, but what the hell does that mean? Okay, a measure is just a PDF. Right. We know, okay, so let's start from the Fourier transform definition. We know that the Fourier transform f of the signal f defined for all t is the following function. So integrate from negative to positive infinite. For f of omega exponential of minus I, omega x, integrating over omega. So if we swap this f, we have the signal f, we have it as some measure p, a non-negative measure p, which is really just a PDF. And then we swap this x with the delta, right? And then we don't have the negative term here. Then we have the Fourier transform of non-negative measure. So what is this? A kernel can be approximated with a probability. For every single kernel, this is an associated probability. Yeah.
So what's the like the relation between signal f and probability p?
Signal f is a probability.
Yeah. So what's the relation for that one and the signal f?
This is the signal.
Yeah. How does convert to from signal? Yeah. How does it convert to probability?
That is based on Bachner's theorem. So, and it's pretty complicated math stuff. And I don't have the capability to run the proof of this. And in the original paper, they don't talk about, they didn't use the term kernel, right? Because back then there was no kernel. But it was like some function. And the eigenmatrix is also definite.
So when is it positive? When there's no kernel?
It's like 1960.
Oh, okay.
1960, 1970 is when its result was published, but people at the time, machine learning didn't come up with SVM yet, so they haven't used kernel yet. It's only in 2007 that people are like, wait, you didn't connect this with kernel. This is kernel. You like have this result. So it's pretty insane. So, I mean, you can already anticipate what's going on because GMM, you can put a GMM in here and you can approximate its probability, right? You just need like some way to approximate probability. And you can find its kernel. Awesome. Okay, let's go through, okay, so we can use this obviously. But this guy, right, he wants to decompose this into this, right? So we're gonna run through how we're gonna do that. Okay, so given this, right, if we integrate over this thing, it's just simply the expected value with respect to omega of the smaller term. And if we do a Monte Carlo sampling, it's just basically we sample omega, from p omega we sample r of them, right? And we sum all of that and divide by 1 over r. So if we do the Euler formula, then we get this from here. And because we're doing a real number, we can get rid of this. And now, okay, so there's 2 ways that you can derive z. This is one way, and there's another way. So I guess I'll just run through this like very quickly. But with this one, so all right, so we have this way. So we need to be able to decompose this loss here into the z something, zx, zy, basically. And so let's define a beta, which is sampled from a uniform distribution from 0 to 2 pi. And then let's add this to the original to x plus y. So instead of x minus y, x plus y. Add this inside the cosine term. And then we know that the expected value of this is equal to expected value of the smaller term with respect to b given omega. And the value of this, so the value inside, if you integrate, right, from 0 to 2 pi, because that's b, right? Actually, this is about to 0. Because you can like take derivative of this and you actually get sine. You take 1 and 2 pi out, and you get sine in here, and then the thing is like part b is going to be equal to like, so there's going to be sine of this term minus sine of this, which is like 2 pi, and you know that like sine is like, if sine of t is equal to like sine of t of like k, k times 2 pi. So actually cancel that because it equals 0. So this whole term equals 0, so this thing equals 0, so this whole term equals 0. So the point of that is just to add this in for free. So if we add this in for free, right, then we can use some trigonometry identity, specifically the cosine of x plus y is equal to cosine of x cosine y minus the sin x and y. If we use that in here and we do some trigonometry manipulation to get this, and you see this is z, and this is z. Zx, zy, right? Alternatively, and then once you get the z, you just do Monte Carlo, and then you get what you want. Well, alternatively, you can also define z to be cosine, cos, in the sine term, and you do Monte Carlo over half. Then you do the matrix multiplication of these two terms, which is the dot product, and then you get this from the cosine identity, from the trigonometry identity, and you get the same thing. So it can be this or it can be this, but we're gonna use this one. People like it, I don't know why. And so if you have the exact RBF kernel, look at this. It's really smooth, right? So this is all the x1 to xn, x1 to xn, all the terms. And if you have like 1 samplings like this, 10 samplings like this, 100 samplings like this, and 1,000. So you see, as you increase it looks closer and closer to the original kernel. And this is an example of using kernel for regression, and you see this is the original kernel. When r is equal to 1, r is equal to 5, and 100. This is already pretty good at r equal to 100. So you don't even need to do the original kernel. And it's linear. And look at the experiments. So with the exact spinner, this thing takes 44 hours. This one takes 71 minutes. Right, this takes 13 minutes, it takes 36 seconds. So it's linear and it's crazy. Okay. So some kernel, so what's the lesson? Some kernel can be estimated using its respective PDF. Because each shift invariant kernel is associated with a PDF. If we can find the PDF, we can find the kernel. And if we can find the kernel, we can find the Z function. And then we can do all the linear stuff that we want and run with it. So to get it, combine with GMM, you get everything you want. So yeah, so I'm just gonna skip the boring stuff. But so all you do is so this is just the equation for Z earlier, right? You sample a bunch of W to do Monte Carlo, and you apply it on the second formulation, which is this one, and which is just R. And then to approximate a PDFP using GMM, you have this one, it's already predefined before. You substitute this into the kernel definition, but this is the original Bottomless theorem. So if you substitute in the Bottomless theorem, you get this term. And now what you do is so now we're not going to do this because this is not linear. So instead, we're going to do the Z, and Z can be defined as RKS of sigma omega, so that's going to be equal to this, right? It's going to be equal to the bottom one. This is going to be the phi that we're going to do. And then for each of the omega, we're going to sample it from the GMM. And with the GMM, we don't even need to do the sampling. And we shouldn't. Why? because you cannot backpropagate sampling from distribution. Some interesting stuff in this if you're interested, but so what we're going to do for GMM, we're going to do vec GMM, is we're going to have some mu plus n times sigma. So that's going to mimic. And we basically have all of these parameters learnable except from n. N we're going to sample at the beginning. This is the trick from the normal distribution. So it mimics the probability of the Gaussian distribution. And then we just, for the weight, we just have it 1 over c. Because the author doesn't want to learn have too many learning parameters. Yeah, results. Accuracy very high, retrieval accuracy very high. Memory consumption a lot lower than the original transformer. And these all these other ones, all the ones that says RPF, RPS, those are the other derivatives of the previous GMM RPS I was talking about, but I didn't mention because it would take too long. Performer and linear LU are two other linearized model, two previous linearized model, except with these ones, they didn't learn the kernel. They just did the exact same thing as the original paper. They defined their kernel function, and then they just use the Boston's theorem to derive phi. So they don't make this learnable at all. Okay, in terms of sequence length, look at this. Transformer, as you increase the sequence length increases so quickly. With these one, I'll increase a little bit. And this one is on long range task. Alright, but on this one, this is short range task on blue. So it still performs as well, but it doesn't perform as well as this one. It still performs really well. So look, so just for accuracy, the softmax of the original transform is 0.81. That was at 0.83 and everything was at 0.0 to 80 to 0.802. So yeah, so I guess what's the point of this? If you can find a way to parameterize the PDF any way that you want, you can learn the kernel. Or you can even use other kernel learning techniques as long as it can be used in backpropagation because many kernel learning techniques were invented in an era where people in that field they don't use neural network. So you can't backpropagate sampling, you can't backpropagate things like that. Okay, what's the lesson? To efficiently train transformer-based models, we need a good attention matrix. Attention matrix needs to be tuned to a data set that relies on the choice of kernel. It is inefficient to manually select the kernel. Kernel can be learned by parameterizing a learnable probability distribution combined with Bachman's theorem. Such a kernel's parameters can be learned during backpropagation while training. Perfect. Yeah, that's it. So yeah, I guess the point is you can learn a kernel, make it more generalized. So, any question?
The last bit is a bit quick. But
Okay, so
So, has this been like put in any like widely used packages? This formulation.
So okay, two things. Number one, this paper was published in 2022.
Okay, so it's quite old.
No, this is recent. This is last year.
Yeah, but like transformer research is crazy.
But the thing is, like, and if you look at the citation, right? Look, it's only cited 7 times. It's like because it's so niche, and also like.
But it has obviously better results. But you would be likely that these kind of results are being used behind the scenes for proprietary models. Use transform architectures.
So the thing is, okay, so have they been put into any packages? The thing with machine learning is like a lot of times you will publish the code.
Yeah.
And who are the users? The users are not going to be people who will be using libraries. They don't use libraries. If they use libraries, that means that they're using really popular model. But if you want to use like really like frontier science stuff, and especially if it's not coming out of Meta or something. Like even sometimes when it's coming out of Meta, not everything's on plugin base. Not everything is like library packaged. Yeah. Then you would probably have to read the code. You probably have to go to the source source code, and you need to figure out how to integrate into your pipeline, because it's not like, and like probably like the one that they have on the so I'll show you like one, like there's some that's good. So for example, like I'll show you like one thing that's sort of related.
GBQ.
This is also a kernel learning technique. Yeah, so for example, this is one of the paper. So it has like the NumPy implementation, the TF implementation. But usually it's not this clean. So for example, you want to detect GPT. It's like I can't use it out of the box.
Yeah.
This is detect GPT.